June 15, 1951, Bingham Canyon, Utah. The engineering report from visiting European mining specialists would never fully capture what they witnessed that morning. An American truck driver named Jake Morrison loading 85 tons of copper ore into a machine that European experts had publicly declared mechanically impossible. Through the dust and diesel smoke of the Utah mining operation, the Euclid R-85 began its climb up grade so steep that European trucks required two separate trips with lighter loads. No complex hydraulics, no electronic systems, no gradual inclines to work with the mountain, just raw mechanical power that defied everything European mining wisdom said was necessary for heavy hauling. In European mines, single-engine trucks maxed out at 8% grades with full loads. Steeper climbs meant backing down and trying again. Most required cooling stops every few hundred yards. The Americans were operating with engineering philosophy the Europeans had dismissed as brute force over-engineering. Twin engines, twin transmissions, 15% grades with full loads, fuel delivery through simple spring-loaded injection pumps that never hesitated when power was needed. 2,000 miles from European proving grounds, the most decisive revolution in mining equipment was revealing itself. Not in sophisticated electronics, not in cautious engineering, but in mechanical systems that delivered exactly what American mining demanded. Arthur Armington stood in the machine shop of Euclid Road Machinery Company on a cold March morning in 1948, holding a telegram that would change American mining forever. The message from Kennecott Copper's Bingham Canyon operation was blunt. Need trucks capable 15% grades, 85-ton payloads. European manufacturers claim impossible. Can Euclid deliver? Arthur read the telegram 3 times before walking to his father's old desk, where George Armington had sketched the crane designs that built their company from nothing after arriving from Scotland in 1895. The problem wasn't new, but the urgency was. Western mining operations had been struggling with the same transportation challenge for decades. Copper deposits in Utah, iron ore in Minnesota, coal seams in Wyoming all required hauling massive loads up grades that conventional trucks simply couldn't handle. European manufacturers like Krupp and Fawn had dominated heavy hauling for generations, but their philosophy centered on working with terrain rather than conquering it. Their trucks climbed gradually, made multiple trips, and accepted the time costs as necessary limitations of mechanical engineering. Hans Müller, Krupp's chief mining consultant, had visited American operations the previous fall and published his findings in International Mining Engineering Monthly. The American approach to heavy hauling reflects their national character, brute force applied to problems that require finesse, Müller wrote. Steep grades demand lighter loads and multiple trips. This is not a limitation of engineering, but a recognition of mechanical reality. No single truck can safely climb 15% grades with full mining loads. Arthur had read Muller's article twice, and each time it reinforced his conviction that European thinking was fundamentally wrong. Distance and terrain in American mining operations made multiple trip systems economically impossible. A copper mine in Utah couldn't operate like a coal pit in Germany. Time was money, and every extra trip cost precious production hours when ore prices fluctuated daily on commodity markets. The solution that had been forming in Arthur's mind for months violated every principle of conventional truck design. Instead of building bigger single engines or accepting payload limitations, he envisioned something no manufacturer had attempted: twin engines, twin transmissions, twin drive axles. Each engine would contribute its own power through its own drive train, essentially creating 2 trucks sharing one chassis. Harold Peterson, Euclid's chief engineer, had initially dismissed the concept as mechanically impossible. You can't synchronize 2 engines to pull together, Peterson argued during their first design meeting in January. One will always overpower the other. The differentials will fight each other. The whole system will tear itself apart. But Arthur had spent weeks sketching mechanical linkages that could make twin engines work in harmony. One throttle cable split to control both engines simultaneously. Mechanical fuel injection systems that would deliver identical power curves. Spring-loaded injection pumps that required no electronic management, just precise mechanical timing perfected through decades of diesel engineering. The specifications that mattered were surprisingly straightforward. Each Cummins 671 diesel engine delivered 250 horsepower through mechanical fuel injection, no electronics, no computer controls. Combined output reached 500 horsepower to move 170,000 pounds gross weight. The power-to-weight ratio of 0.0029 horsepower per pound seemed modest compared to European trucks, but Arthur understood that raw power meant nothing without the ability to deliver it precisely when needed. Peterson had gradually warmed to the concept as they worked through the mechanical challenges. The Allison Torquematic transmissions were proven components in single-engine applications. Each transmission would handle only one engine's power, reducing stress on individual components while doubling total output. The real innovation lay in coordinating two independent powertrains to work as one system. Detroit engineers had arrived in February to evaluate the proposal, and their reaction was predictably skeptical. Twin engines mean double fuel consumption, double maintenance, double everything that can break, argued Robert Hayes from Allison Transmission. Mining companies want reliability, not complexity. But Arthur had convinced Hayes to supply transmissions by pointing out that each transmission would actually work easier than in single-engine applications, since it would handle only half the total power demand. European competitors had learned of Euclid's twin-engine project through industry publications and responded with barely concealed amusement. Muller published a follow-up article titled "American Overengineering: Why More Power Creates More Problems." He argued that mechanical complexity inevitably led to field failures, especially in harsh mining environments where dust, heat, and continuous operation destroyed delicate systems. Proven engineering principles exist for good reasons, Muller wrote. Single engines with robust components remain superior to experimental dual-power configurations. Even Euclid's own board questioned the financial wisdom of twin-engine development. Board member William Crawford had invested in the company specifically because of its reputation for reliable, conventional equipment. "Arthur, your father built this company by delivering what customers needed, not what engineers wanted to experiment with," Crawford argued during a heated March board meeting. "Mining companies need trucks that work every day, not prototypes that might work sometimes." But Arthur understood something that European engineers and conservative board members missed. Western mining operations weren't asking for experimental equipment. They were demanding solutions to real problems that conventional engineering couldn't solve. 15% grades with 85-ton payloads weren't theoretical challenges. They were daily operational requirements that determined whether mines remained profitable or shut down. The first R-85 prototype was scheduled for completion in September 1948. Arthur had committed Euclid's engineering resources and reputation to proving that American mechanical thinking could revolutionize heavy hauling, not through electronic sophistication or complex hydraulics, but through the systematic coordination of proven components in ways European tradition had never imagined possible. The October morning in Arizona brought news that would haunt Arthur Armington for months. Jake Morrison's voice crackled through the telephone from the proving grounds, delivering the report that every engineer dreaded. "The rear axle housing cracked halfway up the 12% grade. Truck rolled backward about 50 feet before I got her stopped." Arthur set down the receiver and walked to the window overlooking Euclid's machine shop, where workers were already building the second R-85 prototype. The failure had occurred exactly as European critics predicted. Hans Muller's detailed analysis, published in Mining Equipment Quarterly just days after the Arizona incident, dissected every aspect of the twin-engine concept's supposed flaws. Excessive torque concentration at differential housings creates stress points that conventional single-engine designs avoid, Muller wrote. The American approach demonstrates why established engineering principles exist, not to limit innovation, but to prevent predictable mechanical failures. Harold Peterson arrived at the factory before dawn the following Monday, carrying photographs of the cracked axle housing and a stack of stress analysis calculations. The damage was extensive but revealing. The axle had split along a welded seam where standard truck components met the extraordinary demands of twin-engine power. "The concept isn't wrong," Peterson told Arthur during their emergency engineering meeting, "but we're asking 1930s truck parts to handle 1950s power levels." Peterson's solution required rebuilding every major component from scratch. Standard rear axle housings measured half an inch thick at stress points. The new design would require 3/4 inch thickness with steel reinforcement ribs running along the housing length. Each axle would carry only one engine's power, but components had to be overbuilt for the combined stress of coordinated pulling when both engines worked together on steep grades. The frame presented even greater challenges. Conventional truck frames consisted of parallel steel rails connected by cross members, designed to carry loads and absorb road shock. Twin-engine power created torsional stresses that twisted frames beyond their design limits. Peterson developed a revolutionary backbone frame concept using boxed steel rails that flex slightly under load, but maintain perfect alignment between twin powertrains. The frame had to be strong enough to handle 170,000 pounds gross weight, while flexible enough to prevent binding between synchronized mechanical systems. Cooling systems demanded complete redesign. Twin engines generated twice the heat of conventional trucks, and mining operations in Arizona and Nevada reached temperatures exceeding 100 degrees Fahrenheit during summer months. Peterson's dual radiator system featured two 24-inch radiators with thermostat-controlled fan clutches that allowed each engine to maintain optimal temperature independently. Combined cooling capacity reached 80 gallons of coolant circulating through separate systems that prevented total cooling loss if one engine failed. The mechanical complexity that European critics had warned about became Peterson's obsession with simplicity. Every control system ran on mechanical linkages rather than hydraulic or electrical components that could fail in mine dust and extreme temperatures. One throttle cable split to control both engines simultaneously through a precision-machined linkage system that ensured identical fuel delivery to each cylinder. Fuel injection remained purely mechanical spring-loaded injection pumps delivering 3,000 pounds per square inch pressure through gear-driven timing that required no electronic management. Jake Morrison returned from Arizona with insights that contradicted the apparent failure. Despite the cracked axle, both engines had performed flawlessly throughout the test. The mechanical fuel injection systems never missed a beat, maintaining smooth power delivery, even as the truck struggled up the grade with damaged components. Those Cummins engines wanted to pull that load, Morrison reported to Peterson. The truck parts gave up, but the engines never did. Winter testing in Ohio revealed additional challenges that European manufacturers had avoided by limiting their trucks to gentler applications. Sub-zero temperatures turned conventional hydraulic fluid sluggish and caused seal failures in standard components. Peterson developed cold weather specifications that went beyond normal automotive standards. Arctic-grade hydraulic fluid rated to -40 degrees Fahrenheit. Reinforced seals that maintained flexibility in extreme cold. Preheating systems that brought mechanical components to operating temperature before startup. The precision required for synchronized twin-power systems pushed 1940s manufacturing beyond normal limits. Every gear had to be machined to tolerances of 1/10,000th of an inch to prevent binding between coordinated transmissions. Standard manufacturing practices allowed variations that would cause twin engines to fight each other rather than work together. Peterson convinced Arthur to invest in Swiss-made precision equipment typically used for aircraft components rather than truck parts. By spring 1949, the second R-85 prototype incorporated Peterson's complete redesign. The truck that rolled out of Euclid's factory bore little resemblance to conventional haulers. Massive axle housings, reinforced backbone frame, dual cooling systems. Every component built to handle stresses that no single-engine truck had ever encountered. The power-to-weight ratio remained unchanged at 0.0029 horsepower per pound, but the mechanical foundation could finally handle 500 horsepower delivered through coordinated twin drivetrains. European observers continued their skeptical analysis through technical publications and industry conferences. Muller's latest article, The Hidden Costs of American Over-Engineering, calculated that twin-engine trucks would require 40% more maintenance than conventional single-engine designs. Mechanical complexity increases exponentially with component count, Muller argued. Every additional system creates new failure points that mining operations cannot afford. But Peterson had discovered something that European analysis missed. The R-85's mechanical systems were actually simpler than European trucks in crucial ways. No complex hydraulic systems, no electronic controls, no sophisticated transmissions designed to compensate for inadequate engine power. Every component delivered exactly what it was designed for, nothing more, nothing less, but nothing withheld when full power was demanded. The rebuilt R-85 was ready for its second Arizona test by June 1949. This time, Peterson accompanied Morrison to the proving grounds, carrying stress gauges and temperature monitors that would measure every aspect of twin-engine performance under the conditions that had destroyed the first prototype. The telegram from Kennecott Copper arrived at Euclid headquarters on May 15, 1951, carrying an invitation that would determine the future of American mining equipment. Willing to test 3 R-85s against current fleet, Bingham Canyon operation, 60-day trial period, must demonstrate superiority over existing European equipment. Arthur Armington read the message twice before calling Harold Peterson and Jake Morrison into his office. This was the moment they had worked toward for 3 years. Real mining conditions, real loads, real competition. Bingham Canyon represented the ultimate proving ground for heavy hauling equipment. The copper mine descended nearly 3,000 feet below the Utah desert, with ore deposits accessible only through winding roads that climbed from pit bottom to crusher stations, at grades reaching 15%. Every ton of copper required hauling 85 tons of ore-bearing rock up switchback roads, where European trucks struggled with lighter loads and frequent cooling stops. Bill Crawford, Kennecott's mine superintendent, had operated the Bingham Canyon facility for 12 years and witnessed every major equipment innovation in mining. His skepticism toward untested American trucks was earned through bitter experience with manufacturers who promised revolutionary performance but delivered conventional failures. "I've seen plenty of experimental equipment that worked fine in Ohio, but died in Utah," Crawford told Arthur during their initial meeting at the mine offices. "Desert heat, continuous grades, 24-hour operations, that's where real trucks prove themselves or break down." The competition was formidable and established. Krupp's K-180 trucks had hauled ore from Bingham Canyon for 8 years with proven reliability. Each truck carried 60 tons with a single 180 horsepower engine, climbing the steepest grades in 47 minutes with mandatory cooling stops every half mile. European engineering philosophy accepted these limitations as necessary compromises between mechanical stress and operational reliability. Hans Müller arrived from Germany specifically to observe the R-85 trials, bringing precision instruments to document what he expected would be spectacular American failures. Mining operations require equipment that performs consistently for years, not experimental prototypes that might achieve impressive short-term results, Müller told Crawford during a pre-test inspection. Twin engines double the maintenance requirements while creating coordination problems that single-engine designs avoid entirely. Jake Morrison prepared for the first test run with systematic thoroughness that had become his trademark. He checked mechanical fuel injection pressure on both engines, 3,000 pounds per square inch delivered through spring-loaded pumps that required no electronic management. Hydraulic fluid levels in both Allison transmissions showed proper viscosity despite overnight temperatures dropping to 28 degrees. Coolant circulation through dual radiator systems maintained optimal flow rates that would prevent overheating during sustained climbing. The moment of truth came at dawn on June 21, 1951. Morrison loaded 85 tons of copper ore into the R-85's reinforced steel bed and engaged both transmissions simultaneously. The truck's gross weight reached 170,000 pounds, 25 tons heavier than any European truck attempted to haul up Bingham Canyon's steepest grades. European observers positioned themselves at strategic points along the climb to document the expected mechanical failures. Both Cummins 671 engines settled into their characteristic rhythm at 1,800 revolutions per minute as Morrison began the ascent. The mechanical fuel injection systems delivered precise amounts of diesel to each cylinder, based purely on spring pressure and cam timing. No computer adjustments, no electronic management, just mechanical precision perfected through decades of diesel engineering. The synchronized twin transmissions shifted smoothly through their gear, ranges while maintaining perfect coordination between independent powertrains. The first critical test came at the steepest section, where European trucks typically required cooling stops or light loads. Morrison maintained steady progress up the 15% grade, while both engines operated at optimal temperature despite ambient heat exceeding 95 degrees. The dual cooling systems circulated 80 gallons of coolant through separate radiators that prevented any single point of failure from stopping the truck's progress. Halfway up the most challenging section, Morrison encountered an unexpected obstacle that would have forced European trucks to abort their climbing attempts. A maintenance crew was repairing road damage directly in the truck's path, requiring a complete stop on the 15% grade. European observers expected catastrophic failure. Conventional trucks couldn't restart from standstill positions on such steep inclines without backing down for a running start. Instead, Morrison brought 170,000 pounds to a complete stop and idled for 3 minutes while the crew cleared equipment. Both engines maintained steady operation at idle speed, with mechanical fuel injection systems delivering exactly the fuel required to keep diesels running smoothly. When the road cleared, Morrison simply pressed the throttle, and both engines responded instantly to power demands without hesitation or strain. The restart from standstill on a 15% grade demonstrated capabilities that no European truck could match. Twin engines delivered synchronized power through mechanical linkages that required no electronic coordination. Spring-loaded fuel injection pumps responded to throttle input with mechanical precision that eliminated the lag time common in hydraulic or electronic systems. The R-85 pulled away smoothly from its stopped position and continued climbing at 15 miles per hour. The time to reach the crusher station established new performance standards for heavy mining equipment, 28 minutes from pit bottom to top, 19 minutes faster than European trucks managing the same climb with lighter loads. No cooling stops, no mechanical strain, no drama beyond the systematic delivery of power exactly when and where it was needed. Muller's precision instruments recorded performance data that contradicted his fundamental assumptions about twin-engine complexity. Both engines maintained identical operating temperatures throughout the climb. Fuel consumption measured 0.47 gallons per ton of ore hauled, actually more efficient than European trucks carrying lighter loads. Mechanical stress readings showed that individual components operated well within design limits despite delivering combined power that exceeded any single-engine truck. Crawford observed the entire test from the crusher station, timing the R-85's performance against his established standards for European equipment. The results were undeniable and immediately significant for mining operations that measured profitability in tons per hour rather than theoretical engineering principles. One American truck had accomplished what required 2 European trucks and significantly more time. The implications extended beyond single test runs to fundamental questions about mining efficiency and American industrial capability. If R-85s could consistently deliver such performance, Bingham Canyon could increase daily ore production by 34% using the same number of trucks and drivers. Success at Bingham Canyon generated orders that transformed Euclid from experimental manufacturer to major mining supplier within 18 months. By September 1952, 50 R-85s operated across Western mining operations from Montana copper pits to Nevada gold mines. Production schedules ran 3 shifts daily to meet demand from companies that had witnessed the Utah trials and wanted their own twin-engine fleets. Arthur Armington expanded the factory workforce from 200 to 800 employees, while Peterson supervised quality control that maintained the precision tolerances essential for synchronized twin power systems. The disaster began with a phone call from Anaconda Copper's Butte operation on a frigid November morning. 3 R-85s down with transmission failures, reported Mine Superintendent Tom Bradley. Cold weather seems to be killing the Allison units. Arthur initially dismissed the report as isolated incidents. Mining equipment always faced harsh conditions that occasionally caused failures. But within days, similar calls arrived from operations across Montana, Wyoming, and Colorado. By December, 17 R-85s had suffered catastrophic transmission failures in sub-zero conditions. The pattern was consistent and devastating. Hydraulic fluid in the Allison-Tormatic transmissions became sluggish below -10 degrees Fahrenheit. Clutch packs overheated as thick fluid created excessive friction. Final drives seized when hydraulic pressure couldn't maintain proper lubrication flow. Trucks that had performed flawlessly in desert heat died completely when temperatures dropped below zero. Hans Müller's response arrived through technical publications with the speed of a man who had been waiting 3 years to vindicate European engineering principles. His analysis, published in International Heavy Equipment Review, dissected every aspect of the transmission failures with methodical precision. Sub-zero operations expose the fundamental weakness of American over-engineering, Müller wrote. Complex twin-power systems create multiple failure points that simple, proven single-engine designs avoid. European manufacturers learned centuries ago that mechanical simplicity provides reliability that no amount of raw power can replace. The financial impact was immediate and potentially fatal for Euclid. Kennecott suspended orders for 200 additional R-85s pending resolution of the cold weather problems. Anaconda canceled contracts worth $8 million. Phelps Dodge demanded full refunds for trucks that couldn't operate during Montana winters. Insurance companies threatened to drop coverage for mining operations using experimental equipment that demonstrated such spectacular failure rates. Arthur faced the most serious crisis in company history during an emergency board meeting called for December 15th. Board member William Crawford, who had initially supported the R-85 project, now questioned the fundamental wisdom of twin-engine complexity. "Your father built this company on reliable equipment that worked in all conditions," Crawford argued. "These transmission failures prove that European critics were right about American over-engineering. We're facing bankruptcy because we ignored proven engineering principles." The human cost of the crisis struck closest to home when Jake Morrison volunteered to test a damaged R-85 under extreme conditions in Montana. Morrison had become the public face of twin-engine success, and his reputation was tied directly to the truck's performance. Against Peterson's explicit warnings, Morrison pushed a transmission-damaged R-85 beyond safe limits during January testing near Butte, where overnight temperatures reached -28 degrees. The incident that followed would haunt Morrison for years. Both transmissions failed simultaneously during a steep descent loaded with 60 tons of ore. Hydraulic systems froze completely, leaving Morrison with no power transmission from either engine to the wheels. Only his quick thinking with engine compression braking prevented a runaway truck disaster that could have killed him and destroyed mining equipment worth hundreds of thousands of dollars. Morrison managed to stop the truck using pure engine braking, but the incident shook confidence throughout the mining industry. Yet Morrison's near disaster revealed something crucial that neither European critics nor Euclid engineers had fully recognized. Throughout the transmission failure and emergency braking, both Cummins engines continued running perfectly. The mechanical fuel injection systems never missed a beat, maintaining smooth power delivery even under extreme stress that would have killed electronic management systems. Engine compression provided enough braking force to stop 170,000 pounds because the diesels themselves were fundamentally sound. Morrison's technical report, filed after the Montana incident, identified the core problem with characteristic precision. The transmissions are asking single-engine components to handle twin-engine power in conditions they were never designed for, Morrison wrote. But both engines ran perfect through the whole thing. The twin-power concept works. We just need transmissions built for twin-power applications instead of modified single-engine units. Peterson's analysis of the failed transmissions confirmed Morrison's observations while revealing the specific technical problems that European critics had failed to identify. The Allison-Tormatic units were designed for single-engine applications where hydraulic systems operated within narrow temperature and stress ranges. Twin-engine power created hydraulic pressures that exceeded design specifications when combined with sub-zero temperatures that thickened hydraulic fluid beyond acceptable viscosity levels. The solution required abandoning modified single-engine transmissions entirely in favor of purpose-built twin-power units. Peterson contacted Allison's chief engineer, Robert Hayes, to propose development of completely new transmissions designed specifically for synchronized dual-engine applications. Hayes initially resisted, arguing that the development costs would be enormous and the market too small to justify the investment. Arthur's response to Hayes demonstrated the determination that had driven him to pursue twin-engine development despite years of skepticism. European manufacturers are telling mining companies that twin-power systems are impossible, Arthur argued during a heated conference call. If Allison builds transmissions that make twin engines work reliably, we'll prove them wrong and own the heavy mining market for the next 20 years. By February 1953, Euclid faced a crucial decision point. European competitors were aggressively marketing their proven single-engine reliability against American experimental complexity that had demonstrated spectacular failures. Mining companies were canceling orders and demanding refunds. The company's survival depended entirely on solving transmission problems that had vindicated every European criticism of twin-power complexity. The irony was bitter but clear. Morrison's insight about engine performance during transmission failure had revealed that the fundamental twin-power concept was mechanically sound. The Cummins diesels delivered exactly the power characteristics that mining operations required. But asking single-engine transmissions to handle twin-engine applications had created the very complexity problems that European critics had predicted from the beginning. Robert Hayes arrived at Euclid headquarters in March 1953, carrying blueprints that would revolutionize heavy equipment transmission design. The Allison engineer had spent 4 months developing concepts for purpose-built twin-power transmissions after witnessing the spectacular failures that had nearly destroyed Euclid's reputation. "We're not modifying existing transmissions anymore," Hayes told Arthur and Peterson during their first design meeting. "The HT750 will be engineered from scratch for synchronized dual-engine applications." The breakthrough design abandoned conventional transmission architecture entirely. Instead of 2 separate transmissions struggling to coordinate power delivery, the HT750 featured twin input shafts feeding into synchronized output systems that maintained perfect mechanical harmony between engines. Each input shaft connected directly to one Cummins diesel, while internal gear trains ensured that power delivery remained coordinated, regardless of individual engine variations. Peterson's analysis of the new design revealed engineering solutions that addressed every failure mode experienced during the Montana disasters. Independent hydraulic systems for each transmission half prevented total system failure if one circuit lost pressure. Arctic-grade hydraulic fluid rated to -40 degrees Fahrenheit maintained proper viscosity in sub-zero conditions that had killed earlier transmissions. Synchronized shifting mechanisms kept both transmission halves perfectly matched through mechanical linkages that required no electronic management. The most innovative feature addressed the fundamental weakness that European critics had identified in twin-power systems. If one engine failed completely, the HT750 automatically disconnected that input shaft while allowing the remaining engine to continue pulling through its dedicated transmission section. Single-engine operation provided reduced power but maintained mobility, a crucial advantage over European trucks that lost all power when their single engines failed. Manufacturing the HT750 required precision beyond normal 1950s production standards. Every gear had to be machined to tolerances of 1/10,000th of an inch to prevent binding between synchronized transmission sections. Standard manufacturing practices allowed variations that would cause twin inputs to fight each other rather than work together. Hayes convinced Allison management to retain Swiss clockmakers who hand-fitted critical components to achieve the precision required for dual-power coordination. The first HT750 prototypes underwent brutal testing at Allison's Indianapolis facility throughout spring 1953. Engineers subjected the transmissions to temperature extremes from -40 to +120 degrees Fahrenheit while applying full twin-engine power loads. Hydraulic systems maintained proper pressure and fluid flow under conditions that had destroyed earlier transmissions. Synchronized shifting operated smoothly through thousands of gear changes that simulated years of mining operations. By May, 20 R-85s equipped with HT750 transmissions were ready for field testing at operations where earlier trucks had failed catastrophically. The stakes couldn't have been higher. Euclid's survival depended on proving that purpose-built twin-power transmissions could eliminate the reliability problems that had vindicated European skepticism about American over-engineering. Bill Crawford at Kennecott had agreed to conduct the ultimate proving test despite his company's bitter experience with transmission failures during the previous winter. "You get one more chance to prove twin engines work," Crawford told Arthur during contract negotiations. 30 days of continuous operation hauling 85 tons up 15% grades, 0 transmission failures, or Kennecott goes back to European equipment permanently. The test began June 1st, 1953, with 20 R-85s operating around the clock at Bingham Canyon. Each truck hauled 85 tons of copper ore from pit bottom to crusher stations 80 times per day, 1,600 total hauls that would stress every component to its operational limits. Ambient temperatures exceeded 100 degrees Fahrenheit during afternoon shifts, while dropping below 40 degrees during pre-dawn operations. Jake Morrison supervised driver training for the new HT750 transmissions, emphasizing the mechanical simplicity that made twin-power systems reliable. "These transmissions want to work together," Morrison explained to drivers who had experienced earlier transmission failures. "Don't fight the system, let both engines find their rhythm, and the transmissions will keep them synchronized." The key was understanding that mechanical coordination worked better than electronic management in harsh mining environments. Hans Müller observed the testing with characteristic skepticism, documenting every aspect of R-85 performance through precision instruments that measured stress, temperature, and mechanical wear. European manufacturers were watching Bingham Canyon closely, understanding that successful American twin-power systems would revolutionize heavy mining equipment worldwide. Failure would confirm European engineering superiority, but success would force fundamental changes in their design philosophy. The results exceeded even Arthur's optimistic projections. 30 days of continuous operation produced 2,400 total hauls without a single transmission failure. Average climb time from pit bottom to crusher remained 26 minutes, 19 minutes faster than European trucks managing the same loads. Fuel consumption improved to 0.44 gallons per ton of ore as drivers learned to coordinate twin engines for maximum efficiency. More importantly, the mechanical systems demonstrated the reliability that mining operations demanded. HT750 transmissions shifted smoothly through extreme temperature variations that had killed earlier designs. Hydraulic systems maintained proper pressure and fluid flow during sustained climbing that stressed every component. Synchronized power delivery eliminated the coordination problems that European critics had predicted would destroy twin-engine systems. Müller's final report, transmitted to Krupp headquarters in July 1953, acknowledged what European manufacturers had refused to consider possible. "American twin-engine concept succeeds through superior transmission engineering," Müller wrote. "Synchronized dual-power systems deliver capabilities that single-engine designs cannot match. Recommend immediate development of competing technology." The admission marked the end of European dominance in heavy mining equipment. By December 1953, orders for R-85s with HT750 transmissions overwhelmed Euclid's expanded production capacity. Mining companies across the American West demanded trucks that could climb 15% grades with full loads while maintaining reliability standards that European equipment couldn't match. The twin-power concept that had nearly destroyed the company now established American supremacy in heavy hauling. The Vindication was complete but costly. 3 years of development, spectacular failures, and near bankruptcy had proven that innovative American engineering could revolutionize industrial equipment. But success required abandoning conventional wisdom about mechanical simplicity in favor of purpose-built systems designed specifically for American operational demands. Twin engines worked, but only when every component was engineered from scratch to handle twin-power applications. Arthur understood that Euclid had accomplished something beyond commercial success. American mechanical thinking had challenged European engineering traditions and won through systematic innovation rather than incremental improvement. The R-85 represented proof that native ingenuity could surpass centuries of established wisdom when applied with sufficient determination and engineering precision.